2.1, here we have the tangent line problem. We have the graph of a parabola shown here. And what we're asking with this is how fast is the graph changing at x equals 1? Whoops. Right here. Okay, how fast is it changing about right there? So, see, a tangent line, remember, from geometry, it would only intersect the function in one spot. Whoops. So we can kind of imagine this line here, and it's just touching the graph right at one point when x equals 1. So we want to know what's the slope of that. And we're going to estimate that right now by finding the slope of secant lines. So we're going to say the first one, 1.5 and 1. And we're going to say, what's the slope of this line? And then we're going to decide to look at 1.1 and 1. So we're going to get a little bit closer. And what's the slope of this line? And eventually, we're going to get so close to that tangent line that the slope of the secant line will eventually match the slope of the secant line. Slope of the secant will match the slope of the tangent. So using your calculator, there's a really nice way of doing this. If you don't know how to put, like, if you put the function into y1, you can actually type on your calculator y1 of 1.5 minus y1 of 1 over 1.5 minus 1. You can type that in. The calculator will figure out the number and do the calculation. If you don't know how to do that, ask. Okay, I'll help you out. But if you do that, we get 1/2 or 0.5 for this slope. And then we get 0.9. And then we get 0.99. And again, 0.999. So based on that information, okay, I'm going to write this out so you can see it as x approaches 1, the slope approaches 1. And that's what it looks like. We don't have any mathematical evidence of that yet, but it's what it appears to be. So now we're going to find the average rate of change, and remember that's just slope, between the points where x is 1 and x is 1 plus a little bit. We're going to call that little bit h. So we're going to have a of h. Our average rate of change between the 2 points is y1 or y2, whatever, minus y1 over x2 minus x1. All right, so then I'm going to go ahead and write this out a little bit. Instead of writing f, I'll write our function. And then minus 3x minus x squared. Don't forget to put the parentheses there. A lot of people do. And then it throws off your sign and it doesn't work. And I already forgot to... No, I think I'm okay. No, I'm not. Okay, so instead of f of x, I'm jumping the gun here. I'm trying to surprise you and it's not working out. Instead of f of x, that clearly says f of 1. So if we plug 1 into that equation, we get 2. So that's minus 2. There we go. All right. Over 1 plus h minus 1 would just be h. Continuing, if I distribute 3 plus 3h minus, I'm going to do this, I'm going to expand it, and then change the sign because we have the negative in front of it. Minus 1 minus 2h minus h squared minus 2 all over h. Keep simplifying. We have 3 minus 1 minus 2. They're gone. 3h minus 2h. That's h minus h squared over h. Okay, look, I can factor an h out of the numerator. All right, so the average rate of change between the points 1 and a little bit is 1 minus h. Okay, what happens to the secant lines between the points as h gets smaller and smaller? Remember, those secant lines kind of start building closer and closer and closer and matching that tangent line. So now we're going to evaluate the limit as h approaches 0. So the limit as h approaches 0 of 1 minus h is 1. So that is what this this whole chapter's based on, this tangent line problem. We're trying to figure out the slope of a tangent line. How fast is something changing at one specific point? Now we could do that to figure out how it's changing at 1. We could do that to figure out how it's changing at 2, or 2.5, or 0. Or we can just get some kind of function instead. And this is what I was trying to do when I made the mistake earlier. So instead of using x and x plus 1, or 1 and 1 plus h, I'm going to use x, just any general x coordinate, and then x plus h. All right, so I'll write out what I'm doing. X plus h minus x. There we go. So we're using that similar method. Here we go. Now I put in x plus h. I can't write. Okay, let's try that again. All right. 3 minus x plus h squared. You want to make sure you keep both parts. And then this is what I was trying to do before. All over h. Expand. Okay, I'm expanding and distributing. All over h. Okay, and it looks like some of these things will start canceling out. We have 3x minus 3x. They're gone. Okay, so I have 3h. Oh, I forgot. Minus x squared plus x squared. Minus 2xh minus h squared all over h. Guess what? We can factor an h out of that. Gone. Okay, and now we had this function. Okay, and we're going to now add that little part. We're going to use that similar method of, as above. We're going to let h approach 0. If we do that, we get this function 3 minus 2x. So this gives us the slope of the tangent line at any point x. We'll find faster ways to do it later, but this is really important. It sounds really confusing, but all we're doing is slope. The whole big idea, everything that we're focusing on here, is change in y over change in x, which is your slope formula. It's just like your 6th grade thing, okay? Your geometry, you did this, pre-calc, you did this, algebra 2, I'm sure you did it. It's just slope. Don't get intimidated by all the letters. All right, so we finished that. We'll do one more example. All right, so this is where the slope, the idea of slope from algebra connects to calculus, when we throw that limit right in the definition. So we have this f prime of x, that's how you read that, f prime, is the limit as h approaches 0 of the change in y values over the change in x, which ends up just being h each time. This is the definition, the limit definition of a derivative, the basis of the first half of calculus. So we can say f prime of x. Okay, later we'll just say y prime or dy dx. They all mean the same thing, but for the first example, we'll stick with f prime of x so you won't be too scared. So we're given a function. We need to find f prime of x using the limit definition of the derivative. So I'm going to make this a little bit smaller. There we go. So we're going to set up. Don't forget the limit. Let me even call it this. All right. F prime of x equals the limit as h approaches 0. It's going to get annoying to write that every time. Too bad. Do it anyway. Okay. F of x plus h. So that would be x plus h minus 2 minus f of x all over h. Okay, so we can't just plug in 0 for h. We'd like to, but then we get 0 over 0, and we know that's a problem. Good thing we had that whole chapter on figuring out how to work with limits. We're going to multiply by the conjugate. Square root of x plus h minus 2 plus square root of x minus 2. And remember, you can't just multiply by anything you want. You got to multiply by 1 if you don't want to change it. Okay, so we do that and bring down that limit. And in the top, we get x plus h minus 2 minus the quantity x minus 2. And in the denominator, we have h times, and I'm just going to leave this alone. Why expand it, right, if you don't have to? Okay, let me clear away this green. Okay, and continuing in blue. Simplify the top. We have x minus x. We have negative 2, positive 2. So it looks like here we have the limit as h approaches 0 of h over h times this quantity. H's are gone. That's great. Now plug in 0 for h. F prime of x equals 1 over, and we'd have square root of x minus 2 plus square root of x minus 2, which you can also write as 1 over 2 square root of x minus 2. Now we have this derivative function. So no matter what value we put in there, we could tell what the slope of the tangent line is at that value. So if we want to do part B, find the slope of f of x at x equals 27, all we need to do is plug in 27 to our derivative function. F prime of 27 is equal to this value. So 1 over 2 times the square root of 25, so we get 1 over 10. Write an equation of the tangent line in Taylor form, and Taylor form is really useful. If you could get comfortable with it now, it'll be great. And remember, that's the point slope, y equals y1 plus m times x minus x1. Okay, we've used that for a long time. It's just point slope form. So we need the slope for the equation. We've got that. We need a point for the equation. So if you plug in 27 to our original equation, you would get square root of 25, which is 5. So we have our x and y value, and we have our slope. Y, that doesn't look like a y. Let's try again. Y equals our y value, 5, plus our slope times x minus 5. And you can leave it just like that, and you're done. There's the slope. There's the equation of our tangent line at the point when x is 27. Lastly, use the equation to determine the values of x for which f of x is differentiable. Remember, it's not differentiable if our derivative is undefined. So first, let's just start with f of x. The domain of this is x has to be greater than or equal to 2. But when we look at our our derivative function, our f prime, oops, we have a similar equation, but this is in the denominator. So x cannot equal 2. So f of x is differentiable for any value for any x value greater than 2, not or equal to. All right, we'll talk more about it, but keep in mind, all we're doing is slope. It's just a fancy way of writing slope. If you focus on that, then this will be a really easy section.